Imagine a message in a bottle, cast into the cosmic ocean not by us, but for us. Perhaps it was left by an intelligence that witnessed the very birth of our solar system. The clues to this ancient story might not be found on our world, but instead woven into the very fabric of Saturn's glorious rings. Our most ambitious robotic explorer, the Cassini-Huygens probe, was dispatched to study this giant world, but what it discovered went far beyond anyone's initial imagination, hinting at profound mysteries that challenge everything we thought we knew. It's truly astonishing how fortunate we are to have had the Cassini-Huygens mission focused on the exploration of Saturn. Although 4 robotic spacecraft have visited Saturn, Cassini-Huygens is without a doubt the most significant, both in its concrete achievements and its scientific revelations. The vast amount of data it sent back has provided the foundation for over 4,000 scientific papers. This incredible mission identified 6 moons that were previously unknown and dramatically deepened our understanding of their makeup. It endured a 20-year odyssey, covering a distance of 7 billion kilometers, and spent 13 of those years in orbit around Saturn itself, carefully gathering data on the planet's gravitational field, its magnetosphere, its complex ring system, and its core structure. Cassini continued to collect information right up to the very last moments of its existence as it began its planned dive into the hazy, mustard-hued clouds of Saturn's atmosphere, where it ultimately broke apart into innumerable fragments. When you consider this tireless acquisition of data, alongside the fact that it captured some of the most stunning and majestic pictures of Saturn and the wider solar system to date, you're left with a mission that is nothing short of spectacular. Come along with us today as we explore a detailed summary of Cassini's grand finale, the vital period leading to its final plunge, the pioneering discoveries it achieved both before and during its descent, and the unending flow of amazing insights that are still being uncovered today from the precious clues that Cassini-Huygens provided. For any person wanting to genuinely grasp the magnificent beauty of Saturn, there's no better way than to see it through the eyes of Cassini during its breathtaking grand finale. The initial probe to make it to Saturn was the Pioneer 11 spacecraft in the year 1979. It was throughout this groundbreaking mission that scientists were able to definitively establish that Titan, which is Saturn's most massive moon, had a thick atmosphere. This crucial finding highlighted the need to go back and investigate the moon in more detail, but on the next visit, with a lander specifically designed for the task. At that point in time, Voyager 1 and Voyager 2 were already traveling towards Saturn, which made it unfeasible to add a lander to those missions already in progress. For this reason, the Cassini-Huygens mission was developed, and in October of 1997, it was successfully sent off into the blackness of space. Sending a spacecraft all the way to Saturn is a profoundly difficult task, as the entire trip was a continuous battle against the sun's gravitational influence, which was constantly trying to pull Cassini back toward the inner solar system. To build up the enormous speed required to get to Saturn, Cassini cleverly used planets as gravitational slingshots. It performed 2 careful flybys of Venus before swinging back around to Earth. Our planet's gravity then served as a powerful catapult, flinging it out toward Jupiter, which provided the last essential boost needed to arrive at Saturn. This specific celestial arrangement of planets, which made these necessary gravity assists possible, happens only one time every 600 years, emphasizing just how important the timing was for this mission. Cassini's second pass by Earth was especially close. At its nearest point, it flew just full 100 kilometers above our planet's surface. This detail becomes even more fascinating when you learn about the power source that kept Cassini running. It was fueled by 3 RTGs, which stands for radioisotope thermoelectric generators. In essence, its power came from about 33 kilograms of radioactive plutonium. It was the steady radioactive decay of this element that gave Cassini its constant energy, and even near the very conclusion of its operational life, it was still producing roughly 700 watts of power. A major point of concern tied to a spacecraft carrying such a large amount of radioactive material was the disastrous possibility if scientists' math had been incorrect and the probe had come crashing down on Earth. In that terrible event, every single person on the globe would have been exposed to the radiation. While 33 kilograms spread over the entire Earth is a tiny amount, in the absolute worst-case situation, NASA projected it might have led to around 5,000 deaths related to cancer. In spite of this serious potential, they decided it was a worthwhile risk because the chance of such an event happening was an incredibly small one in a million. Cassini had to use RTGs because solar panel technology of that era was simply not developed enough to effectively power a spacecraft at such a great distance from the Sun. With RTGs, Cassini was guaranteed a very long operational duration, and it might even be working to this day if it hadn't eventually used up all its propellant. Cassini was tasked with many ambitious goals: to figure out the complex structure and dynamic nature of Saturn's rings, to investigate Saturn's moons in greater detail, to accurately map Saturn's magnetosphere, to carefully examine Saturn's atmosphere, and to study Titan more thoroughly. This last goal is where the Huygens part of the Cassini-Huygens mission played a crucial role. Huygens was a specialized lander that was attached to the Cassini spacecraft, built specifically to look into the conditions beneath Titan's murky concealing clouds. Huygens itself was the portion of the mission created and managed by ESA, the European Space Agency. This probe was fairly small, measuring only about 1.3 meters across and weighing 300 kilograms. After it separated from the orbiter, it traveled on its own for 22 days before it reached Titan's atmosphere. At that vital moment, the only system running on board was a wake-up timer, which was set to turn on the probe just 15 minutes before it entered the atmosphere. And when it did power up, the views it captured were truly incredible. The main purpose of the Huygens mission was centered around this 2.5-hour descent, and during this time, it gathered essential readings on atmospheric pressure, composition, and wind speed, along with other data. Since the mission was focused only on taking atmospheric measurements, the battery wasn't intended to last much longer than the landing itself. Scientists had guessed that the probe might set down on an ocean or lake, and had therefore built Huygens with that in mind. However, from what was seen, it landed on what looked like the bed of a lake that had dried up. The mission for Cassini itself has been incredibly fruitful. On top of the priceless scientific information it gathered over those 13 years, it also took some of the most magnificent pictures ever captured from space. I want to point out a couple of my own personal favorites of Saturn, and naturally Saturn's moons, which are beautiful in their own unique ways. Some amazingly committed people have even put together over 1 million photos taken by Cassini to make visualizations that recreate what it would be like to be on the Cassini spacecraft. These are real images simply adjusted for color, sharpened, and put in sequence to show movement. There is absolutely no CGI used, which is just breathtaking. As Cassini's fuel supply began to run low, scientists started thinking about the best way to get the most data possible out of the time that was left. To do this, they sent commands to Cassini, telling it to perform a number of extremely close flybys of the planet and some of its moons, getting nearer to Saturn and its rings than it ever had before. Starting on November 30th, 2016, Cassini repeatedly flew high above Saturn's North Pole, then dove down to a spot just outside the thin F ring, which is the outer boundary of the main rings, completing 20 orbits in total. After that, on April 22, 2017, Cassini would make a bold jump over the rings, starting its final series of daring dives between the planet and the inner edge of the rings. This was the start of the Cassini Grand Finale, a sequence of complex loops and dives that brought the probe closer and closer to its subject, facing greater dangers with every pass, until at last, as its data became exceptionally pure, Cassini would finally fall into Saturn's gravitational pull, its destruction becoming a certainty. NASA's website explains the thinking behind this climactic mission. As it dives past Saturn during the grand finale, Cassini will collect a stunning amount of incredibly rich and valuable information, insights that the mission's original planners might have never even imagined. The spacecraft is set to create detailed maps of Saturn's gravity and magnetic fields, which will reveal the planet's internal structure and possibly help solve the long-standing mystery of how fast its interior rotates. It will greatly improve our knowledge of how much material is in the rings, getting us closer to figuring out where they came from. Cassini's particle detectors will directly sample icy ring particles that are being drawn into the atmosphere by Saturn's magnetic field, and its cameras will take spectacular, extremely close-up pictures of Saturn's rings and clouds. No other mission has ever explored this special region so close to the planet. The information gathered from these activities will significantly help to improve our understanding of how giant planets and entire families of planets are formed and to change over time throughout the universe. At the very end of its final orbit, as it fell into Saturn's atmosphere, Cassini would finish its 20-year mission by making sure that the potentially life-harboring worlds of Enceladus and Titan would never be contaminated by tough microbes that might have secretly survived the journey unharmed. It's an inspiring, adventurous, and truly romantic ending, a perfect conclusion to this exciting story of discovery. But let's look more closely at some of these key final moments during Cassini's grand finale. NASA became willing to put Cassini's unprecedented closeness to Saturn above its long-term existence. This was a simple choice to make, as Cassini was already getting low on fuel, making its continued survival an unlikely possibility anyway. Making this choice gave Cassini the go-ahead to get closer to the planet than ever before, weaving skillfully between its rings. But what did it see? Did this special viewpoint show us anything we had never seen before? Let's look at some of the amazing sights Cassini saw during its grand finale. Starting with Saturn's moons, Cassini saw some of the shepherd moons with incredible detail. This picture shows a close pass of Atlas, a 40-kilometer-wide moon that's near the outer part of the A-ring. What's especially noticeable about this moon is the clear lack of impact craters on its seemingly smooth surface, which makes it look utterly strange. Dust from the rings is building up all over its surface, particularly around the moon's equator, which is smoothing it out and giving it its unique disc-like shape. A similar thing is happening with Pan, the second closest moon to Saturn, which is 30 kilometers across and is located inside the Encke Gap. Any particles from the rings that wander into its 350-kilometer-wide orbital path are effectively gathered up by Pan, which is how the Encke Gap is kept stable and at a consistent width. Daphnis is another one of the shepherd moons, which unfortunately wasn't seen in as much detail, but its influence, because of the gap it is in, can be seen for hundreds of kilometers. It is only 8 kilometers in diameter and is found in a very thin gap in the A-ring called the Keeler Gap. Its gravitational force, while extremely faint, is just strong enough to gently pull away nearby dust particles as it goes by. This action creates noticeable waves or a ripple effect in the rings next to it, and sometimes it even pulls material directly out of the ring, which can be seen as a faint trail in this picture. These ripples don't just move from side to side, but also up and down, as you can tell from the shadows they make. One can only try to picture what it would be like to be on Daphnis, watching waves follow its orbital path with the magnificent Saturn and its many moons in the background. It would surely be an amazing thing to see. Speaking of the rings, Cassini was able to get some truly amazing pictures. One of my favorites from the grand finale is this specific photograph, which shows the Janus Type 1 spiral density wave. Amazingly, what you're looking at here is the result of the exact same process that creates spiral galaxies, just on a much more tightly wound scale. What looks like many different rings is actually just two spiral arms that are wrapping around the planet many times. So every other line you can see in the picture is part of the same spiral arm. This particular image is a piece of the B ring at a spot where the ring orbits twice for every single orbit of Saturn's moon Janus, which creates an orbital resonance. This photo makes it look like the image is tilted away at the top left, but that's not what's happening. The illusion is made by the way density waves spread out from the planet, with the wavelength getting progressively shorter the further it gets from the resonance. And this is where the resonance gets even more incredible. Janus, the moon that helps create this resonance, switches places every 4 years with its neighboring moon, Epimetheus. Each time this switch happens, the rings react by making a new crest in the waves. NASA says that the distance between any two crests is equal to 4 years of the wave moving downstream from the resonance. This means that the wave seen here holds many decades of the orbital history of Janus and Epimetheus. Based on this, the part of the wave at the very top left of this picture matches the positions of Janus and Epimetheus around the time of the Voyager flybys in 1980 and 1981, which is exactly when Janus and Epimetheus were first confirmed to be two separate celestial bodies. This method of encoding information is reminiscent of the way a tree trunk's rings record its years of life. It's simply unbelievable. Besides other magnificent and detailed pictures of the rings, other fascinating sites have included these small propeller features dotted throughout the rings in different places. This specific image shows both sides of the rings. The top picture shows the lit side, while the bottom picture shows the unlit side. Scientists use this method to compare and try to see fine details. Even though the image scale is about 500 meters per pixel, the moonlet itself might not be visible. One might only be able to see a faint hint of it in the top picture. However, what is clear is that the moonlet is physically tied to the rings by a band of material. As stated, this wasn't the only moonlet trying to make a gap in the rings. Here's another one, right next to the Encke gap, and here's another, probably the biggest of the three. None of these moonlets are thought to be larger than 2 kilometers in size, and they probably have the density of a snowball. The last interesting observation Cassini was able to picture within the rings has to do with extremely small but solid objects that have formed around the E-ring, possibly started by the gravitational disturbances of some of the nearby shepherd moons. They seem to be solid because they've survived many collisions with the E-ring, throwing out dust and particles that sometimes even follow their orbit, as you can see by the haze around them. The objects themselves aren't actually visible because of the obscuring dust. Finally, let's direct our focus to the planet itself. Since Saturn's northern hemisphere was in the middle of summer at the time of Cassini's flyby, its amazing hexagon located around the pole was in plain sight. At the middle of this hexagon is a permanent polar vortex, which contains the eye wall of a giant hurricane. Interestingly, the pole seems to be going through a seasonal color shift, as can be seen clearly when compared to 2012, when the pole looked quite dark. With the help of other wavelengths of light, more storms can be seen scattered across the planet, as well as bands similar to Jupiter's, though not as bright in natural light. Furthermore, because Cassini was so close to the planet, it got an excellent look at the planet's horizon. On the left side of the picture, a haze can be seen in the stratosphere of the atmosphere, which fades away toward the right side of the image. When Cassini finally did enter the atmosphere on its last approach, it was first believed it wouldn't even make it to this haze. However, scientists weren't too worried about that. Of special interest to scientists was the exact composition of the atmosphere. Cassini would dive into that atmosphere to get this vital information and would be destroyed in the process, marking the last data Cassini would ever send. However, 1 week before it entered the atmosphere, Cassini was still busy taking pictures. Some of these last images are truly fantastic, though it's important to remember that Cassini wasn't able to capture real-time video. The videos you're about to witness are time lapses, the careful piecing together of countless individual pictures into glorious visualizations of what it would have been like to travel with Cassini on its final journey into Saturn. Not all of these pictures are of Saturn itself. The first time-lapse we'll look at is from September 8, 2017, just a week before the end of Cassini's mission. One of Cassini's main focuses during its mission was the moon Enceladus, which is thought to be one of the best candidates in the solar system for possibly hosting life in an ocean beneath its surface. Cassini found over 100 water plumes shooting up through the moon's crust from this ocean, water that freezes in the vacuum of space and has now created the magnificent E-ring around Saturn. This ring is incredibly faint, only able to be seen when lit from behind by the sun, and is possibly the bluest naturally occurring thing in the solar system. Here's a great view of Enceladus's effect on the thickest part of the E-ring. You can see the plumes disturbing and refilling the ring. Cassini's last observation of Enceladus's plumes was taken in this amazing time-lapse, captured over a 14-hour period. On September 11th, Cassini was near the most distant point of its last orbit and took this beautiful mosaic in natural light. You can see the thickest of Saturn's rings, D, C, B, A, and F, with Saturn's short shadow falling across them. Saturn's northern hemisphere was in its summer during this time, which means that Saturn's most famous hexagonal storm is visible in all its splendor. You can also just make out Saturn's faint bands in natural light. What's really fascinating about this picture, though, is that the night side of Saturn is faintly lit. This happens because of light bouncing off the rings, which means that Saturn's nights in the hemisphere facing the sun don't get completely dark. Below the soft light of the rings, Saturn is a deep black. As Cassini started to get closer to Saturn again on September 12th, it took pictures of Saturn's atmosphere near the planet's terminator line. Incredibly, because the sun is so low in the sky here, huge cloud structures can be seen making shadows that stretch for many kilometers. One might think this is a close-up of Saturn, but we're actually looking at a scene that's about 5,500 kilometers across Saturn. Its moon Titan could easily fit inside this picture. Cassini was getting ever closer to Saturn. On September 13th, it took one final look at Daphnis, and sharp-eyed observers will see ripples both in front of and behind the moon. This is because of the different orbital speeds of the rings and the moon. The inner ring orbits faster than Daphnis, so the ripples overtake the moon, exposing more ring material to the moon's gravity. On the other hand, the outer ring moves slower than Daphnis, causing the ripples to fall behind the moon. By the time the ring material gets to Daphnis on either side again, the ripples have already flattened out. On that same day, Cassini took one last panoramic picture of the Saturnian system. It got a view of Titan, a moon it had focused on a lot during its mission. A truly remarkable world with a thick nitrogen atmosphere. It also saw Saturn's rings, with the uneven F-ring just barely visible at the bottom of the picture. And as Saturn got bigger and bigger, it took one last look at Enceladus over a 40-minute period before it disappeared from sight behind the edge of Saturn. The very last picture Cassini ever sent was a view over the area where it would finally dive into the atmosphere. It was nighttime there, and so Saturn was lit up by light reflecting off the rings. On its final day, taking pictures wasn't on the scientists' minds. As lovely as they are, images use up a lot of precious bandwidth, and scientists wanted to get every last bit of real-time data before the spacecraft was inevitably destroyed. This was a unique and unprecedented chance. We had never directly sampled Saturn's atmosphere before. When Cassini first hit the thin outermost layers of Saturn's atmosphere, it was moving at an incredible 123,000 kilometers per hour. The last bits of Cassini's fuel were carefully used by its thrusters to keep the spacecraft's antenna pointed at Earth. At this point, Cassini was 1,900 kilometers above Saturn's clouds. A minute later, these thrusters were firing at their full power to keep Cassini from spinning out of control. Cassini was directly sampling Saturn's atmosphere, but this atmosphere was also creating immense heat on the spacecraft. Just 10 seconds later, the thrusters were overpowered and Cassini started to tumble, cutting off communication with Earth. Cassini's onboard computers at this moment would have been frantically trying to figure out what was happening. Gyroscopes and star trackers would have told the computer that it was spinning, and it would likely have gone into a safe mode, redirecting power to try and reorient itself. A minute or so after that, the spacecraft would have completely broken apart and burned up in Saturn's atmosphere. When the data started to arrive 1.5 hours later on Earth, this final part of the mission was clearly declared a huge success. Cassini recorded data from direct analysis of Saturn's atmosphere, its ionosphere, dust particles in the atmosphere, and from magnetic field readings, and maybe even more insights that still need to be fully discovered from the massive data set. And that is the truly incredible thing about the Cassini mission. It keeps producing new scientific papers and discoveries as the data it gathered is carefully analyzed and looked at again. What have we discovered from Cassini's data in the years since its historic mission came to an end? You're about to find out, but be warned that some of the things Cassini has revealed about Saturn have only made the planet even more of a puzzle. You might think you have a handle on Saturn. Its famous rings are the biggest in the solar system, and its hazy yellow surface is both enigmatic and instantly recognizable. It's the second biggest planet, the least dense, and the sixth from our Sun. And still, Saturn remains a complete mystery. A deep puzzle is hidden underneath its obscuring atmosphere, a puzzle that the Cassini probe brought to light, one that the scientific community still can't agree on. Saturn acts in ways that our standard models say are impossible, from its temperature to its magnetic field, and even the exact length of its days. What is really going on with Saturn, and what are our best efforts to explain these confusing phenomena? The Cassini probe got to the gas giant on July 1st, 2004. It wasn't the first probe to arrive at Saturn. 3 others had already done flybys. However, as noted before, it was by far the most thorough. It spent 13 years carefully circling the planet, gathering huge amounts of data with its various spectrometers. magnetometers, and other special tools. The knowledge it has given us has been hugely beneficial, yet sometimes it just makes Saturn's mysteries even deeper. Think about, for example, that hexagon storm at Saturn's North Pole. The edge of this 29,000-kilometer wide storm could easily fit Earth's diameter inside each of its sides. And as far as we can tell, it doesn't move its longitude, staying fixed in its spot, moving along with the planet's rotation, unlike the rest of Saturn's swirling clouds, which are pushed by its winds, hitting speeds of up to 1,800 kilometers per hour. The storm is definitely strange. Scientists haven't come up with a full explanation for it yet, though some lab experiments have managed to create things that look a lot like hexagons on much smaller scales. But it's not the only mystery. As the mountains of Cassini's data started to be analyzed in the years after the mission ended, more puzzles began to appear. It started with a seemingly simple question: how long is a day on Saturn? Even though we've been watching Saturn in our night sky for thousands of years, scientists still didn't have a solid answer. After all, it wasn't as easy as just looking at the planet and figuring out how long it took for its rocky core to spin. Saturn's thick cloud cover hides any landmarks that might be on a solid surface below, and those clouds move at different speeds compared to the core because of strong winds. The rings themselves orbit Saturn at different speeds, so they don't help solve this problem. You can't just watch their orbital speed and think it matches the core's rotation. After all, most moons don't do this, so rings are no different. Rather cleverly, scientists have ways of figuring out the rotation of a gas giant by looking at its magnetic field. It was hoped that this technique could be successfully used on Saturn. Planets that have magnetic fields create them through a dynamo effect. As the planet spins, liquid metal in its core also spins and moves, and this huge motion of molecules creates immense currents of energy, which then make magnetic fields. A key feature of this process is that, because of this rotation, the pole of the magnetic field is always offset from the planet's axis of rotation. If the two were perfectly lined up, the magnetic field wouldn't last for very long, so all you have to do is detect the magnetic fields around a planet, which Cassini could do, and watch as the magnetic pole traces a circle around the planet's true axis. Once the magnetic pole makes one full rotation, you found the length of its day. Only Saturn, as it turns out, doesn't play by these rules. Its magnetic pole is almost perfectly aligned with its axis of rotation, with an incredible degree of accuracy, less than 0.1 degrees. And even though dynamo theory says this alignment should be impossible, Saturn's magnetic field is strong and active. Its magnetic moment is 5 to 80 times stronger than Earth's and has a very powerful effect on the Saturnian system as a whole. Scientists are confused about how this magnetic field is created, as it's considered impossible under the current dynamo theory. Yet no other known method for making such a field has been proven either. A planetary dynamo is definitely at work in Saturn's core, but some other effect must be happening in the atmosphere to bend the magnetic field lines, making them perfectly aligned with the axis of rotation. Or we're seeing a completely new way of generating a magnetic field on Saturn. So it was back to square one for figuring out the length of a Saturnian day. Luckily, radiation turned out to be more helpful. Saturn is an electrically active system. Charged ions move between the layers in its atmosphere, and even between its rings and its ionosphere. Scientists noticed that Saturn gave off radio waves because of all the magnetic fields at play, and these radio waves changed in strength. In fact, it seemed to match what one would expect to see as a result of the planet's rotation. Higher levels of radiation would show up about every 11 hours. Because of this, scientists concluded with some confidence that this was Saturn's day length. Their first guess, based on Voyager data, was 10 hours, 39 minutes, and 23 seconds. It was hoped that Cassini would be able to make this number more accurate. At first, Cassini was able to do that, but then things got really confusing because over the 13 years that Cassini studied Saturn, this number started to change. It drifted by about 1% over a year, sometimes getting longer, sometimes shorter. This almost seemed to mean that the planet itself was changing its rotation speed, sometimes speeding up and sometimes slowing down. To be clear, a planet as huge as Saturn shouldn't be doing something like that. So scientists decided that this wasn't really happening, and some other atmospheric effect must again be hiding the true picture around Saturn. Some part of the atmosphere was causing shifts in the fields, making the radiation fluctuate over time, and hiding the planet's real rotation under a shimmering cloak. Another key result of the planet's magnetic field is the auroras that flicker at Saturn's poles. However, while on Earth our auroras are caused by solar wind interacting with our atmosphere, it's thought that this doesn't fully explain the auroras on Saturn. Cassini found that at least some of them happened regardless of the solar wind's activity at the time, which means that Saturn's auroras are non-solar in origin. Something strange must be going on inside Saturn. It was also hotter than it should be. It radiates out into space about twice as much energy as it gets from the sun. While some of this can be explained by the gravitational compression of the planet, the rest needed another explanation. In the end, all of these observations needed a single explanation, and interestingly, thanks to Cassini's data, we found that the key to all of it might be in Saturn's gaseous atmosphere. Saturn is a gas giant. It's almost entirely made of hydrogen and helium. Not all of this is in a gaseous state, as the huge mass of Saturn means that the deeper you go into its atmosphere, the more intense the heat and pressure get. It's thought that this pressure forces gaseous hydrogen to turn into liquid metal. Some scientists think that this liquid hydrogen, or maybe even hydrogen, pressed so tightly that it becomes diamond, rains down into Saturn's depths, and the friction from this process explains some of Saturn's unusual heat. However, the rest of the heat comes from the auroras. Although these are not fully understood, it's believed that they are the result of electrically charged particles coming into Saturn from its rings and moons. No matter where they come from, these auroras may be creating enough heat to warm the planet's upper atmosphere. Such high temperatures create other effects. Where warm fronts meet cold fronts, strong winds are formed. It's believed that these winds carry charged ions around Saturn's upper atmosphere, and these electrically charged winds are what is messing with the data from Saturn's radiation, causing it to vary. Perhaps such movement of electrical currents might also explain why Saturn's magnetic fields are not where they're supposed to be. This could be caused by a conductive layer in Saturn's clouds moving at a different speed than the others, creating fields of their own. At least, that's the current explanation. In all of this, it should be clear that many of these answers don't have definite proof. Scientists are carefully going through the data provided by Cassini, hoping for more clues. If these clues don't appear, then eventually another mission to Saturn will be needed to find the answers to these confusing questions. But what about the length of Saturn's day? Thankfully, this one mystery does have an answer, and it turns out the clue was in the rings all along. Instead of looking at the electrical and magnetic influence of Saturn on its rings, scientists realized that Saturn would also affect them through its gravity. This is pretty obvious, but what was more insightful was that Saturn wouldn't pull on them with a uniform gravitational force. Saturn is not a perfect sphere. Any change in its shape causes variations in its gravitational field. Saturn's rings were a perfect canvas to see such variations, as Saturn pulled at its rings with a changing force. At certain spots in the rings, it would be possible to see ripples. Scientists started looking for these ripples and found them by measuring the distance between them. It was finally possible to calculate the exact length of Saturn's day. They weren't far off. It was 10 hours, 33 minutes, and 38 seconds. And this time, scientists are pretty sure that they have the right number. So at least this one mystery was solved, and yet Saturn's other deep mysteries still remain. The next mission to Saturn is planned to launch in 2027 with NASA's Dragonfly, though this mission will mainly focus on exploring Titan, Saturn's biggest moon. Titan is the most Earth-like object in the solar system, as it's the only place known to have an atmosphere full of nitrogen like ours, though without oxygen, and with rain cycles and liquid lakes on its surface, though these are made of methane instead of water. So, it's understandable why scientists are eager to check it out further. Still, it means that it may be a while before Saturn's deepest mysteries get their answers. Saturn breathes. The winds that might be the lifeblood of the system hum and flow across its atmosphere. Its delicate balance of magnetic fields and gravity coaxes its rings, keeping them perfectly aligned. Saturn's rings are thought to be surprisingly young. Saturn itself might be over 4 billion years old, but there's evidence that suggests the rings may have formed only in the last 100 million years, and they are slowly disappearing back into Saturn's atmosphere. So in another 100 million years, they might be gone. This idea is a bit sad, but I also feel a strange sense of luck. If humanity hadn't come along when we did, we might have missed this amazing cosmic show. It may be unscientific to say that a planet has no real choice in whether it gives us a gift, but I'm still grateful to have been a witness to the mysterious and wonderful world that is Saturn. And seeing those mysteries and wonders, all the beauty, all the scientific data, simply wouldn't have been possible if it hadn't been for the incredible Cassini-Huygens mission. This truly was one of the greatest space missions of our time. Jupiter, a world of giant storms, deadly radiation, and captivating beauty. A cosmic giant whose huge mass is so great that it even has an effect on the Sun itself. Jupiter is quickly becoming one of the most studied objects in our solar system, with 7 flybys, 2 orbiters, one of which is still working today, and 2 more planned missions. There's an incredible amount to learn about the 5th planet from the Sun. What gives it its unique red color? What is its exact makeup? What is hidden under its obscuring clouds? What do we know about its famous Great Red Spot? Jupiter plays a very important role in protecting our solar system, and it's time to explore its deep mysteries. Come with us today as we explain everything you could possibly want to know about Jupiter, the 5th planet from the Sun. Jupiter is located on the edge of the asteroid belt, sitting between the orbits of Mars and Saturn. It is, on average, 778 million kilometers away from the Sun, or 5.2 astronomical units, and it completes 1 orbit every 12 Earth years. The planet's axial tilt is very small, just 3 degrees. This slight tilt means it has very little seasonal change. Unlike Earth and Mars, and much like Saturn, its radius at the equator is larger than at its poles. It is a truly huge planet, the largest in our solar system. Its mass is so great, 1,000th that of our Sun, that while that might not sound like a lot at first, once you realize the Sun has 99. 86% of all the mass in the solar system, you'll understand that Jupiter makes up almost all the rest. Its mass is 2.5 times that of all the other planets in the solar system put together. This leads to an interesting phenomenon. The barycenter between Jupiter and the Sun is actually located above the Sun's surface, at 1.068 solar radii from the Sun's center. Let's talk briefly about barycenters. When we think of one object orbiting another, we don't usually consider that the smaller object has a gravitational pull on the larger object. This is because most of the time the effect is tiny, like the International Space Station orbiting Earth, or even Mercury orbiting the Sun. However, this effect does still happen. A barycenter is the center of mass between two orbiting objects, or the point in space that both objects orbit around. With Jupiter's huge mass and its distance from the Sun, unlike Mercury, its effect is far from tiny. As Jupiter swings around the Sun, both celestial bodies do a subtle dance around this center of mass, which is, in fact, located above the Sun's surface. Let me show you this principle with an example. If I take a heavy object and a less heavy object and connect them to the ends of a long stick, for the stick to balance, we have to find its center of mass. As you can see, the center of mass is closer to the heavier object. Imagine this is the Sun and Jupiter, with the stick being gravity, and you'll understand how a barycenter works. While Jupiter has the most mass of any planet in the solar system, it's not the densest. It's the most massive because it's the largest. If Neptune were the same size as Jupiter, it would be the most massive. And if Jupiter were the same size as Earth, Earth would be over 4 times more massive. As it is, however, Jupiter's diameter is 11 times that of Earth, and its total mass is 318 times greater than Earth's. As we know, mass affects gravity. This means that Jupiter has a huge gravitational pull, more than twice that of Earth, at 2528 g at its surface. The gravity of Jupiter is so strong within the solar system that it affects every other planet to different degrees. Its gravity is strong enough to rip asteroids apart and has captured at least 67 moons. Some scientists even think that Jupiter destroyed numerous celestial objects in the ancient past, as well as stopping other planets from forming. One specific example of this is Vesta. Scientists even predict that Jupiter's gravity is so significant throughout the solar system that it's disturbing Mercury's already eccentric orbit enough that, in a few billion years, the tiny planet might either crash into the Sun or be thrown out of the solar system completely. At the moment, however, it could be seen as the protector of the 4 inner planets. Without Jupiter acting as a cosmic vacuum cleaner, it wouldn't be soaking up dangerous objects like long-period comets or disturbing their orbits enough to give them a slight energy boost, making them leave the solar system entirely. Jupiter is the 5th planet from the Sun, and it is 5 times farther away from the Sun than Earth. Even so, it can be the 3rd brightest object in the night sky, beaten only by the Moon and Venus. I just want to show how bright that is. Using just a handheld camera, we can quite easily see Jupiter in the night sky. With a maximum magnitude of 2.94, it's actually able to cast shadows. Because of how noticeable it is in the sky, it makes a great target for amateur astronomers. And as consumer telescopes have gotten better in recent years, it's amazing what details you can see from your own backyard. And what causes these famous patterns? The cloud layer is only about 50 kilometers thick and is made of ammonia crystals, much like on Saturn. However, the color comes from compounds that heat up deep inside Jupiter and then rise. These compounds are known as chromophores, and when they reach the clouds, they interact with the sun's ultraviolet light to create these spectacular multicolored bands. This is a very dynamic cycle, and Jupiter's look can change a lot over time. Even if their colors do change, the actual latitudes of these bands stay consistent enough to be given identifying names, though their widths can change over time. Many storms and areas of turbulence happen where these bands meet, and this is the underlying reason and driving force behind Jupiter's very famous Great Red Spot. This storm is enormous. It could easily fit the diameter of Earth inside it. It has been around for as long as we've known it existed, since it was first discovered in the 17th century, and it might very well be a permanent feature of the planet. However, interestingly, its size has gotten smaller since observations started. The reason for its reddish color is still unknown, and the spot's color can change a lot, from a brick red to almost white. The most recent theory about its color suggests that chemical compounds are being broken down by the sun's ultraviolet light in much the same way as the process that happens across the rest of the planet. The storm is actually located much higher in the atmosphere than the surrounding clouds, and as a result can interact with sunlight to a much greater degree. This would explain why its color can be much more intense than anything else around it. But Jupiter doesn't just have one scientifically interesting storm. Another storm, known as Red Spot Jr., we formed when three storms merged into one between the years 1998 and 2000, and it has, so far, passed unharmed by its larger neighbor, now being quite a prominent feature of the planet. It could last for another couple of hundred years if it manages to avoid the same fate as a similar storm that passed right through the middle of the Great Red Spot. So, what do we think Jupiter is made of? Well, much like Saturn, under the atmosphere are gaseous, then liquid, and then metallic forms of hydrogen. The deeper you go into the planet, the greater the pressure becomes. Under immense pressure, hydrogen acts like a metal, and under that, there is an ice or rocky core. Because we can't recreate the huge pressures felt by Jupiter here on Earth, we don't really know the exact properties these materials have at the core. Roughly 90% of Jupiter is thought to be hydrogen, 10% helium, and then tiny amounts of methane, ammonia, and other elements. Jupiter spins incredibly fast, faster than any other planet, making a rotation in only 10 hours. However, because it's not solid, it doesn't rotate at the same speed across its whole surface. A rotation at the poles takes 5 minutes longer than at the equator. As a child, I was very curious about why Jupiter wasn't a star, given its huge mass and its main composition of flammable hydrogen. Surely, someone just needed to throw a match in to light it up. Well, the disappointing news for my inner child is that stars don't work that way. Furthermore, there's barely any oxygen on Jupiter to allow for combustion. Stars create their heat from nuclear fusion, which is started by the extreme pressures found at their cores. Current scientific thinking suggests that Jupiter would need to be about 75 times more massive than it is now to have enough mass to become a star, although interestingly, its volume is not drastically different from that of the smallest known red dwarf. And yes, you might have noticed in this picture that Jupiter does indeed have rings, nothing on the grand scale of Saturn's, but there are 4 planetary rings. The main ring is extremely thin but very bright. The others are quite wide but exceptionally faint. The main ring is about 6,000 kilometers wide, and the only distinct feature one will see in it is what is known as the Métis notch. Something else to note about Jupiter is its remarkably strong magnetosphere. It is 14 times stronger than Earth's, which is due to the planet's liquid metallic hydrogen core. This makes it the strongest magnetosphere of any planet in the solar system, beaten only by the sun's sunspots. There are a couple of reasons why this is particularly interesting. First, magnetospheres channel solar wind toward the planet's poles, which creates magnificent auroras. Second, Jupiter's 4 largest moons are protected from this solar wind because they orbit inside the magnetosphere. This means they don't need their own strong magnetospheres, as Jupiter provides that protection for them. However, this doesn't mean they are safe from radiation. Jupiter has a powerful radiation band around it. the very radiation band that has crippled every probe that has gone through it. Io, the closest large moon to Jupiter, passes right through the middle of this radiation band, getting 3,600 rem per day on its surface. For context, anyone exposed to this level of radiation would die within 4 hours, definitely not the most welcoming environment. When it comes to the Jovian moons, I'll only briefly mention them, as I've made a separate video dedicated to them. Jupiter has 67 known natural satellites. 51 are less than 10 kilometers in diameter. However, the largest, the Galilean moons, Io, Europa, Ganymede, and Callisto, are among the biggest in the solar system, and each is fascinating in its own right. Ganymede is, in fact, the largest moon in the solar system and has a larger diameter than that of Mercury. With this final thought, take a look at Jupiter through infrared light, showing the immense size and power of this planet. This small dot at the bottom of the planet shows the impact of an object from space, which, if it had hit Earth, could have meant the end of our planet as we know it. We can be thankful for Jupiter's presence, not only for its inherent beauty, but also because, in many ways, it serves as an invaluable asset to our solar system. Uranus, this cool bluish-gray marble, looks like a desolate expanse in the far reaches of the solar system. But in reality, there are some truly fascinating facts about this planet that make it different from anything else in our solar system. Join us on this exploration as we reveal almost everything you could possibly want to know about Uranus. The first unique thing about Uranus is its name. All the other planets are named after Roman gods, except for Uranus. It's named after the Greek god of the sky, Uranos. The Latinized version of this word is what we use today. If they had just kept the Greek version, it might have avoided some awkwardness, as people often have trouble pronouncing Uranus in a polite way. It even has 2 accepted pronunciations, as no one has completely agreed on the matter: Uranus and Uranus. Uranus is also truly one of a kind in the way it spins and orbits. It's the 7th planet from the Sun and the second to last planet. It orbits on average about 19. 2 astronomical units from the Sun, which means it's over 19 times farther away from the Sun than our Earth. This distance changes throughout its year by 1.8 astronomical units, the biggest difference of any planet. Being this far from the Sun leads to incredibly cold temperatures, out 220 degrees Celsius, making it the coldest planet in the solar system. Its year lasts 84 Earth years. When it was first discovered, astronomers tried to predict its orbit. After some time, however, they realized it had moved from their predictions and figured out that the reason was the gravitational pull of another, still undiscovered planet. They mathematically predicted where this planet should be, and because of that, Neptune was discovered. Interestingly, the same theory is currently around a yet-to-be-discovered Planet X or Planet 9. Some distant objects in our solar system are not in their expected places, and theory suggests this is because of the gravitational pull of another unseen planet. The search is now actively on to actually find this planet. What is truly captivating about Uranus is its rotation. Most planets spin like a spinning top on the table of the solar system's plane. Not Uranus? No, Uranus has, for all intents and purposes, fallen over and is rolling instead. For large parts of its year, its axial tilt is 97 degrees. This extreme tilt means its seasons are completely wild compared to the rest of the planets. During its solstice, or the time of year when the sun is highest or lowest in the sky, one hemisphere of the planet is always facing the sun, while the other is in total darkness. It almost looks like the planet is rolling along its orbital path. Only a very narrow strip near the planet's equator gets day and night during this time, but even there, the The sun barely comes up over the horizon. The poles, on the other hand, go through 42 years of constant darkness, followed by 42 years of daylight. During its equinox, which is the opposite of a solstice, the planet has a more normal day-night cycle. Uranus is currently coming out of its equinox, having passed it in 2007, and is now moving back toward a solstice. Uranus completes one rotation about every 17 hours and 14 minutes. However, because its surface isn't solid, some parts of the atmosphere rotate faster than others, and because of high winds, some sections can complete a full rotation of the planet in only 14 hours. This strange rotation and axial tilt mean it's the only planet in the solar system that gets more energy from the sun at its poles than at its equator, on average. For some unknown reason, though, the equator is hotter than the poles, and no one fully understands why. There's also speculation about the original cause of Uranus's unique rotation. While it's generally accepted that a large Earth-sized planet crashed into Uranus, knocking its rotation onto its side. How large exactly is Uranus? Well, it's the least massive of the gas giants at 14.5 Earth masses, compared to Neptune's 17 Earth masses. Its diameter, however, is just a little larger than Neptune's at 50,024 kilometers, about 4 times that of Earth. Because this mass is spread over such a huge area, the gravity on Uranus is only slightly less than on Earth, at 7.8 meters per second squared, or 0.89 g. That would feel quite comfortable. And what is it made of? Well, it's believed to have a core slightly smaller than Earth's, made of rocky silicate material, which is surrounded by a mantle of water, ammonia, and methane ices. Although called ices, this mantle is, in fact, extremely hot, reaching almost 5,000 degrees Celsius, and is more like a liquid ocean around the core. So, to call Uranus purely a gas giant is a bit misleading. It's certainly not gaseous all the way through. The atmosphere is, in fact, quite small in comparison, making up only a total of 0.5 Earth masses, with most of Uranus's mass being in this core and mantle. The atmosphere is mostly made of helium, hydrogen, and 2.3% methane. A cloud layer then sits on top of these gases. It is this methane that gives Uranus its unique aquamarine or cyan color. Very interestingly, some models suggest that the pressure at the bottom of the mantle on Uranus is strong enough to break apart the methane molecules, which then presses the carbon atoms from the methane into diamonds. These diamonds would then rain down through the mantle like hailstones. The very bottom of the mantle could possibly be a layer of liquid diamond or carbon, with solid diamond bergs floating in it. We'll now move away from the planet a bit to look at its planetary ring system. Uranus, much like the other larger planets in our solar system, has rings. It has 13 very dark and young rings. Most are not wider than a few kilometers, and they're thought to be only 600 million years old, much younger than Uranus itself. They're made of extremely small particles, the largest being only a few kilometers across, made of water ice and dark, radiation-processed organics. Their albedo doesn't go above 2%, meaning, in other words, they're darker than wet soil. As we'll soon see, Uranus has many moons, and the rings are thought to be the result of high-impact collisions with some of these moons in the past. It's still not clear why some of the rings stay so narrow. The usual explanation is that the rings are kept in place by shepherd moons, but this is only the case for one of the rings here. Uranus was found to have rings in 1977 when an occultation of a star happened. The star dimmed a few times on either side of Uranus as Uranus moved in front of it, which confirmed the presence of rings. Uranus has only been visited by a spacecraft once, and that was in 1986 by Voyager 2. Voyager 2 discovered many of Uranus's rings and moons, giving us close-up pictures of the faint ring system. When Voyager flew by, this only brought the total number of known rings to 11. When the Hubble Space Telescope was launched, it also looked at Uranus, discovering 2 more rings that had never been seen before. The outermost ring is twice as far away from Uranus as the previously thought outermost ring, and, as promised, here is a look at the many moons of Uranus. Unusually, the moons are named after characters in English literature. Overall, Uranus has 27 known moons, put into 3 groups: the 13 inner moons, 5 major moons, and 9 irregular moons. The inner moons are closely connected with Uranus's rings, some of which may have provided the ring's material. The largest of these moons is named Puck, measuring only 162 kilometers in diameter, and it's the only inner moon to be captured in detail by Voyager 2. Interestingly, these inner moons constantly disturb each other, and the system is very unstable. There is a high chance that some of them may crash into each other again in the future. The 5 largest moons, in order of increasing distance from Uranus, starting from the left, are Miranda, Ariel, Umbriel, Titania, and Oberon. Titania is the largest moon of Uranus and the 8th largest moon in the solar system at 1,600 kilometers. Again, as can be seen, these are very dark objects, with Umbriel being the darkest except for Miranda, which is mostly made of water ice. The rest are thought to be a mix of water ice and rocky materials. These moons may have differentiated interiors, which means a core of rocky material surrounded by a mantle of ice, and between the core and the mantle, there could very well be an ocean layer of liquid water. Interestingly, the axial tilt of the large moons is the same as Uranus's, meaning that during a solstice, if you were to look at the sun, it would only ever move in a circle in the sky, never setting during that solstice. Only one side of the moon faces the sun, leading to continuous daytime. The final 9 known moons are irregular moons. They are likely captured objects and are located much further out than the last of the big moons, Oberon. They range in size from 20 kilometers to the largest, Phoebe, which is about 200 kilometers in diameter. Finally, let's explore Uranus's climate and magnetosphere. Uranus's seasons are quite unique in the solar system because of its exceptional axial tilt. Telescope technology has only allowed us to resolve details on Uranus's surface for the past few decades, which makes it hard to say for sure if there are consistent changes between Uranian years. What has been seen, however, is that as the planet gets closer to a solstice, the pole brightens and a distinct color forms moving away from the solstice, the pole, and color dim. This brightness is thought to be because of the thickening of methane clouds, although the exact cause is not clear. Seasons also affect storms in the upper atmosphere. Storms are relatively rare on Uranus compared to other gas giants, but are believed to be caused by seasonal changes. With improvements in telescope technology, we have also been able to see bands stretching around the planet, much like the other gas planets. However, these bands are mainly visible in the infrared spectrum, which is why Voyager was only able to show them to us in visible light. In these infrared images, you can also see small storms dotted all over. Another unique feature of Uranus is its unusual magnetosphere. Typically, magnetospheres come from the geometric center of a planet, but that's not the case with Uranus. Furthermore, it's not aligned with the rotational axis, but is offset by 59 degrees. This strange placement means the magnetosphere is much stronger at the North Pole than at the South Pole. One theory for this anomaly is that the liquid diamond ocean could deflect the magnetosphere, or even that the magnetic field is not generated in the planet's core at all, but rather by the liquid mantle. The magnetosphere is about as strong as Earth's, and because of its unusual rotation, the magnetotail corkscrews off for millions of kilometers into space. Look up into a clear night sky with your naked eye, and what planets would you be able to see? Technically, you would be able to see all of them at one time or another, all of them except for Neptune. It's the smallest of the gas giants and also the farthest away, and it is a perplexing place. You might assume that a planet so distant from the Sun would not have a dynamic atmosphere showing colossal storms and incredibly fast winds, and yet it does. So why is this planet as intriguing as it is? Today we are going to dive into everything you could possibly want to know about Neptune. Let's start right at the beginning. Neptune is the only planet found through mathematical prediction. You see, when Uranus was discovered and astronomers were carefully plotting its orbit, they noticed that Uranus was not sticking to their models. From the disturbed orbit of Uranus, Urbain Le Verrier in 1846 concluded that there must be another, as yet undiscovered planet, and he predicted its exact location. Remarkably, Johann Galle was able to find it only a degree away from the predicted spot. Triton, Neptune's largest moon, was discovered a few days later. However, since then, Neptune has been poorly understood as its huge distance from Earth and its very small apparent size made it incredibly hard to study from ground-based telescopes. It wasn't until 1989, when Voyager 2 arrived, that a lot of information about the planet became available. Suddenly, we could see what the planet looked like, confirm that it had planetary rings, and discover many previously unknown moons. But let's focus on today. What do we now understand about this planet? Since Pluto's reclassification from a planet, Neptune is the eighth and farthest planet from the Sun. It orbits, on average, at 30 astronomical units from the Sun, meaning it is 30 times farther away from the Sun than Earth's orbit. 30 astronomical units, in other words, is 4.5 billion kilometers, and from that you can understand why it would take a space probe using current technology 13 years to reach Neptune. 4.5 billion kilometers is a considerable distance. Because of this long orbit, it takes a huge 165 years to complete one orbit around the Sun, which means we have only seen one Neptunian year since its discovery. This distance from the Sun means the average temperature in Neptune's atmosphere is extremely cold, 201 degrees Celsius. Its axial tilt is 28 degrees, meaning it's similar to Earth and Mars, which have axial tilts of 23 degrees and 25 degrees respectively. This means it has seasons like Earth and Mars, with the big difference being that these 4 seasons each last 40 Earth years. At this moment, the southern hemisphere is in its spring. During this spring, the southern hemisphere gets more sunlight and looks brighter. This increase in brightness is actually quite noticeable, which is strange, as one would have thought that because the Sun is 900 times dimmer on Neptune than on Earth from that distance, it wouldn't have much of an effect. But even if it's only a small effect, it makes an effect nonetheless, and the increased sunlight levels in the southern hemisphere warm it up by about 10 degrees Celsius compared to the rest of the planet. This comparatively higher temperature releases frozen methane into the stratosphere, causing its increased brightness, whereas elsewhere on the planet, it stays frozen and remains deeper in the troposphere. Just a quick recap of the layers of a planet's atmosphere. The troposphere is the lowest atmospheric level, followed by the stratosphere above it. Above those layers are the mesosphere, the thermosphere, and then the exosphere. But that's a very interesting topic in itself, and we'll save it for another video. If you think about the weather on Neptune, it actually has the fastest wind speeds of any planet. With winds blowing westward on the equator, reaching an astonishing 2,160 kilometers per hour, nearly a supersonic flow. And intriguingly, most winds travel retrograde to the planet's rotation. Bands are also formed on the planet, as well as colossal storms. When Voyager 2 passed by the planet in 1989, it saw the Great Dark Spot, a storm about the size of Earth, moving across its atmosphere. Voyager also detected a smaller storm known as the Small Dark Spot, located south of its larger sibling. As Voyager 2 got closer to Neptune, this smaller storm changed in shade from dark to light. When the Hubble Space Telescope was launched, astronomers were curious to find out the fate of these storms, to see if they were a permanent feature like Jupiter's Great Red Spot. However, when Hubble was pointed at Neptune in 1999, these storms had completely disappeared, and storms have appeared and disappeared ever since. Giant, bright, high-altitude clouds also come and go. But why then doesn't Uranus, which is very similar in composition and size to Neptune, also have such a blustery atmosphere? Make no mistake, wind speeds on Uranus are also fast, but they don't compete with Neptune's, reaching only 900 kilometers per hour. Can all this only be blamed on interactions with the Sun and its seasons? Something else must be going on here to explain the extremes in weather. The answer may lie deep under Neptune's surface. I mentioned that Neptune is the farthest planet from the Sun, so you might have thought it's also the coldest, but actually, Uranus is the coldest planet in our solar system. Neptune radiates heat from within, whereas Uranus radiates hardly any extra heat at all. This could be because a large Earth-sized body crashed into Uranus billions of years ago, which used up all of its primordial heat. Astronomers now theorize that the more active weather on Neptune might be due in part to this higher internal heat. What is Neptune actually made of then? Its internal structure and atmosphere are thought to be very similar to Uranus's. Its atmosphere is mainly made of 80% hydrogen and then 19% helium, with very small amounts of methane. It is this methane, however, that gives Neptune its blue color, although it's a darker shade of blue compared to Uranus's cyan. Again, like Uranus, there is a liquid mantle of water, ammonia, and methane ices around the core. And where the core and the mantle meet, the pressure is so huge that the methane may break apart, and diamonds are formed under the pressure, likely not diamonds as you or I know them, but there could be a liquid carbon ocean with solid diamond bergs floating in it, and diamonds raining down through the mantle like hailstones. This is just a theory, however, as technology has only recently started to recreate such pressures. Around the core of Neptune, it's thought to be 7 million bar, or 700 gigapascals, which is about 7 million times the pressure of Earth's atmosphere at the surface. Even the two ice giants' magnetospheres have similarities. Neptune's magnetic field is offset by 47 degrees relative to its rotational axis. When Voyager 2 discovered this about Uranus, the first theory was that it had something to do with its unusual axial tilt. But then it found the same thing about Neptune, which has a more normal axial tilt. So the current theory is that the magnetic field is either not generated in the core, but rather by an electrically conducting liquid mantle, or that the mantle deflects the magnetic field from the core, which gives it this strange offset in relation to its rotational axis. Every planet in the solar system does not, in fact, have a perfectly aligned magnetic field. Even Earth's magnetic north is different from where the North Pole actually is. But it is only Uranus and Neptune that have such a tilted magnetosphere. Auroras also exist on Neptune, but they are different from what one might expect, as they are extremely faint, because particles don't get as charged from the Sun, and because of the direction of the magnetosphere, They are mainly Type B auroras, or SAR arcs. Earth also has these, but they are not visible, and one needs scientific instruments to see them. They could be stretching across the entire sky without you even knowing they're there. Another difference with Neptune's SAR arcs is that they are not only found around the poles, but are rather located around the mid-latitudes of the planet. Zooming out from Neptune a bit, we see its ring system. Like all other gas giants, Neptune does have a ring system, although it is extremely faint, as it is not as dense and is exceptionally dark in color. If you have these rings against the black background of space and also have them located this far away from the Sun, then they are very difficult to see. But there are 5 known rings in total, and they are named after individuals involved in the discovery and research of Neptune. The innermost is the Galar ring, which is very faint and very wide at 2,000 kilometers. Next is the first bright ring, Leverrier. Although it is bright, it is only 113 kilometers wide. Next and connected is the Lassell ring, a very faint band 4,000 kilometers across. On the edge of this ring is the Arago ring. It is slightly brighter than the Lassell ring and less than 100 kilometers wide. Lastly is the outermost and most extensively researched ring, the Adams ring. It is only 35 kilometers wide, but is one of the brightest rings. It is particularly interesting, as it is slightly inclined and has bright arcs within it. These arcs have remained quite stable since their discovery in 1980, but typically planetary rings are uniform throughout. These arcs must represent material clamping and clustering within the ring, but the reason for this is currently unknown. Lastly, I want to talk about the moons. Neptune has 14 known moons, which are named after water deities in Greek mythology. The most famous, and by far the largest, is the moon Triton, which actually makes up most of the mass of all of Neptune's moons put together. I personally think it's one of the most beautiful moons in our solar system, as it shows astonishing patterns and a burnt orange color. What is most intriguing about Triton is the fact that it orbits in retrograde and also at an inclination to Neptune's rotation, which means it is likely a captured object and not something that formed along with the planet. Triton might even be the cause of Neptune's rings, as it would have disrupted the orbits of other moons, possibly causing them to collide and break up into what is now the debris of the rings. Triton is even larger than Pluto and also has a tenuous atmosphere. Voyager 2 even saw faint clouds during its flyby of the moon. The next largest moon is Proteus, which has a slightly irregular shape. Normally, we only see this on smaller objects like asteroids, but Proteus is actually larger at 400 kilometers across than the spherical moon of Saturn, Mimas. The reason for its non-spherical shape is explained by past collisions of objects hitting the moon, leaving behind the massive craters you now see. The inner irregular moons orbit around the rings, some acting as shepherd moons. The outer irregular moons are all likely captured moons. Some of the irregular moons orbit prograde and others retrograde. The outermost moons of Neptune are Sam and Neso, and they are the farthest out satellites of any planet that we know of to date. They take a massive 25 years to orbit Neptune just once. This is because Neptune has a very large hill sphere, the hill sphere being the region in which the planet's gravity overcomes the gravity of the Sun. It has such a large hill sphere because it is already so far from the Sun. The Sun's gravity has less of an influence around Neptune than it does at the biggest planet, Jupiter. Thank you so much for watching this far. Did you learn something new and interesting about Neptune today? What mysteries would you like to see solved? We are still diligently working our way through remastering the planets in our Solar System series. Which planet would you like to see us feature next for this series? Let us know in the comments below, and we'll see you next time.